Imagine predicting the chemical behavior of elements just by knowing their atomic structure. That's the power of understanding electronic configurations. This essay provides a crash course on determining the electronic configurations of the first 20 elements. Atoms, the building blocks of matter, consist of a nucleus containing protons and neutrons orbited by electrons. These electrons reside in specific energy levels or shells, and within each shell, there are subshells, S, P, D, F, with different energy levels. The way these electrons are arranged in various subshells is what we call electronic configuration. By understanding this language, we can predict how atoms will interact, form bonds, and create the incredible diversity of molecules in our universe. So let's delve into the rules governing electron placement and explore how to determine the electronic configuration of the first 20 elements. Each subshell is denoted by a letter, S, P, D, or F, and can hold a specific number of electrons. The S subshell holds a maximum of 2 electrons, P holds 6, D holds 10, and F holds 14. These subshells are filled in a specific order, starting with the lowest energy level. This order is governed by the Aufbau principle, which states that electrons fill orbitals with the lowest energy first. Another crucial rule is Hund's rule, which states that electrons prefer to occupy different orbitals within a subshell before pairing up. Think of it like this: electrons, being negatively charged, repel each other and prefer their own space. Hund's rule tells us to fill each box in a subshell with 1 electron before putting 2 in any one box. With these basic rules in mind, we can now start deciphering the electronic configurations of the first 20 elements. Let's start with the simplest atom, hydrogen, H, which has only 1 proton and 1 electron. Its electron configuration is 1s1, indicating that its single electron occupies the first energy level, 1, in the S subshell. Moving to helium, He, with 2 electrons, both electrons fill the 1s orbital, giving it a configuration of 1s2. Things get slightly more complex as we move to lithium, Li, with 3 electrons. The first 2 electrons fill the 1s orbital, and the third electron occupies the 2s orbital, resulting in a configuration of 1s22s1. As we progress through the periodic table, we continue filling orbitals based on the Aufbau principle. For example, beryllium, B, has a configuration of 1s22s2, boron, B, has 1s22s22p1, and carbon, C, has 1s22s22p2. Notice that with carbon, we begin filling the 2p orbitals, following Hund's rule by placing 1 electron in each of the 3 2p orbitals before pairing them up. This pattern continues as we move to the third period with sodium, Na, having a configuration of 1s22s22p63s1, and magnesium, Mg, having 1s22s22p63s2. The beauty of the periodic table lies in its organization, which directly reflects the electronic configurations of elements. Elements in the same group, or vertical column, have the same number of valence electrons, which are the electrons in the outermost shell. This similarity largely dictates their chemical properties. For example, alkali metals in group 1 all have 1 valence electron, making them highly reactive. Similarly, halogens in group 17 all have 7 valence electrons and are highly electronegative. The periodic table also reflects the filling of different subshells. The S-block elements, which include groups 1 and 2, have their valence electrons in the S subshell. By recognizing these patterns and understanding the relationship between electronic configuration and the periodic table, we can predict the chemical behavior of elements. Memorizing the electronic configurations of all elements can be daunting. However, there are some helpful tips and tricks to make the process easier. First, remember the order in which subshells are filled, known as the Aufbau principle, and the maximum number of electrons each subshell can hold. Second, familiarize yourself with the periodic table and its organization. The periodic table is your cheat sheet. Notice the patterns in electronic configurations within groups and periods. Third, practice writing configurations for various elements, starting with simple ones and gradually moving to more complex atoms. Visual aids, such as orbital diagrams and the periodic table, can be incredibly helpful in visualizing electron placement. By consistently practicing and understanding the underlying principles, you can master electronic configurations and unlock a deeper understanding of atomic structure and chemical behavior. Electronic configuration forms the bedrock of our understanding of chemical bonding, reactivity, and the properties of elements and compounds. By deciphering the arrangement of electrons within atoms, we gain insights into the forces that govern the interactions between atoms and the formation of molecules. This knowledge is fundamental to various fields, from materials, science and drug design, to environmental chemistry and beyond. By mastering this skill, we equip ourselves with a powerful tool to navigate the fascinating world of chemistry. So embrace the challenge, practice diligently, and unlock the secrets hidden within the atom.